Hello, it's me, Mr. Herb, and today we're going to talk about U substitution. Now, U substitution is essentially the chain rule of integration, right? You use it everywhere. It's one of those things that once you learn, you realize that all other integration you've done have been baby play until then. So we're looking at this one. It says, consider the derivative f of x is equal to cosine of 2x. I hope that by chain rule, we all can say that f prime of x would be equal to negative 2 sine of 2x. So this would be negative 2 sine of 2x. And so U sub is works a little bit like this. It says, hey, here's our integration. We're going to talk about the integration of negative 2 sine of 2x. And again, they factored the negative outside. You can have it inside, you can have it outside. It doesn't matter what you want to do. Essentially, what we say is U is equal to 2x. And what that means is if we want to take the derivative of U with respect to x, this would look like du dx. And that would equal 2. However, as you know, this is not, we don't have du dx somewhere in this integral. And so instead we say, well, let's solve for dx. So du equals 2 dx. That's just me multiplying dx on both sides. And then finally I divide by 2. Now again, this is an aggressive amount of steps, but this is us just explaining what's going on. So dx is equal to du divided by 2. Now, let's sub that all in. We know what U is. It's 2. Let's sub dx in. Or sorry, it's 2x. U is 2x. We're going to sub dx in. It's du over 2. And this now looks like negative integral 2 sine of U du over 2. And you probably just make this negative, the integral sine of U du. And boom, you say, hey, I know how to integrate the sine of U. That's just negative cosine. And this negative cosine out front makes this just cosine of U. And of course, because we're integrating, we put plus c. However, a lot of times we don't want to actually use U. We want to use the variable we actually had along the way, which is just 2x. So this becomes cosine of 2x plus c. Again, I want to reiterate that this is an aggressive amount of steps, and you wouldn't really write all of this every time. You'd probably just say, oh, I'm going to call this U, and then that means I have to cancel that out, and this becomes du. And you kind of start from maybe something like this, write this line here. I'll do this in blue. You'd start with this, write this line in blue, and probably jump all the way down to this step. And so all these steps kind of condense just down to 3. Something else I want to make sure we're all on the same page of, and it's when we are dealing with the integral, and a lot of this is indefinite, what we've seen so far, which is, that's why we have that plus c. But let's say instead this was something like, I don't know, pi over 3 and pi over 2. And it was negative 2 sine of 2x dx. Now, we've already stated that this is just cosine of 2x. But if I want to evaluate this integral, we're doing that from pi over 3 to pi over 2. And so now we're just going to plug these bounds in. So this would look like cosine of 2 times pi over 2 minus cosine of 2 times pi over 3. We always, always, always put this top bound first. We plug that in, and then minus the bottom bound. Because again, these are just x values. We're finding the position. We're going to subtract them. So this would look like cosine of pi, which we know is negative 1, minus the cosine of 2 pi, which is negative, I think, 1/2, negative 1/2, in fact. And so that looks like just a negative 1/2 is our final answer. Okay, so be aware if we have bounds, if we're not just doing this, just kind of, if we have bounds on our integral, then we're going to have to plug those values in. There's not just going to be a plus c. Okay. Oh, it's a, yeah, if we're doing a definite integral, that's what I'm looking for. I can say words. Okay, here's the general definition of integrating with u sub. Essentially, if you have f of g prime of x times g prime of x dx, then that's the integral of f prime of u du, which is equal to f of u plus c, which is just equal to f of g of x of c. So really, you realize, hey, inside my parentheses here, I have this whole other function, and I need to get rid of that. A lot of times this will also look like you'll realize you have some type of multiplication and you're trying to undo it. Some of these problems are something you actually hit on in ABC or BC calculus, but we're going to hit some of the more basic ones here. Okay, so let's look at some of these problems. And if you want to pause the video here and try these out, you can. But if not, just follow along. So this is a prime candidate for u substitution because I have an issue with this x squared plus 1 to the fourth. That's going to be tough to integrate because of the plus 1. And I also have an issue with this 2x. We're not really able to undo integrals with products just yet. And so to get rid of that 2x, we're probably going to have to use some type of u substitution. So I'll say u is equal to x squared plus 1, which makes du dx equal to 2x. Notice how that plus 1 goes away as soon as we take that derivative, which is super helpful for us. So that means du over 2x is equal to dx. And then what we can say is, hey, let's replace dx with this du over 2x. So I can still integrate as long as I have that du. And then let's replace x squared plus 1 with u. So the 2x gets canceled out as we replace dx. And so this looks like a du. And the x squared plus 1 gets replaced with a u. And if you can't see, it's because I put a box around it, but it's actually u to the fourth. So now we're going to essentially get rid of the power rule here, right? We're going to undo taking the derivative u to the fourth. So that looks like u to the fifth over 5. Plus c, of course, because we're doing an indefinite integral. And then the last thing we have to do is actually replace u with this x squared plus 1. And so that looks like x squared plus 1 to the fifth all over 5. And of course, still, we cannot forget the plus c. I can't get rid of it. We got to keep it. It's always there. It's haunting us forever. Plus c. All right, the next one. When we're trying to attack this, we say, okay, clear case, sine of 5x is going to, or the sine is kind of my parentheses. The 5x is going to be my u sub. I think this is one where I wouldn't even necessarily do u sub, though, to be honest. I'd probably just be like, oh, if I undid the derivative, I'd get rid of that 5 out front. But we'll show you how to do it with u sub. So here, u is equal to 5x, which means du dx is equal to 5. Which means that dx is equal to du over 5. So now we're going to replace that dx with du over 5. So this 5 is going to cancel. And this looks like the integral of sine of u du. What's the antiderivative of sine of u? Well, you better believe it's negative cosine of u. And then again, plus c, forever staring into your soul. Last, we need to replace u back again. Let's use that 5x. So this becomes negative cosine of 5x plus c. Okay, one more of these. This one's a little bit trickier. We have a tangent that we're dividing by and a secant on top. Ooh. We might try to see if we could simplify that down right from the very get-go. It might help us out. But you never know. I think it might also just be easy to try to do u sub here. So let's instead say, okay, well, do I know either one of these derivatives, right? So when I'm thinking about u sub, I'm thinking about, okay, what could I take and what's it going to cancel out? For example, this tangent right here. Well, what's the derivative of tangent? Well, you better believe it's secant squared. And so if I say u is equal to the tangent of x, then secant squared of x is equal to du dx, which means dx is now du over the secant squared of x. We got to take that sucker, plug that in for dx, and now this becomes the integration of 1 over u du. Ho, ho, ho. Now, please remember the integration of 1 over u is going to equal the natural log of the absolute value of u plus c. However, u is this whole tangent. So this becomes the natural log of the absolute value of the tangent of x plus c. Yikes. That's a lot going on. Got a natural log, an absolute value, and a tangent. What a function. Okay, so here are some basic trig identities when dealing with integration. We've already dealt with the sine and cosine. That's pretty straightforward. However, the tangent, the cotangent, the secant, and the cosecant, a little bit harder to deal with. These are things that probably wouldn't hurt you to memorize, but a lot of time we can also deal with some U-sub to help us out. I think the secant and cosecant are a little bit more difficult to deal with, but the tangent and cotangent really aren't that bad. Let's look for example. So we're going to show how we would prove both of these. Notice how this is tangent of u du. Again, we can integrate as long as these variables match, right? As long as my independent variable is also du on the outside. So if I were to say this is tangent of u du, I go, okay, well, there's nothing for me to cancel out. And the problem is I could really rewrite this as sine of u over cosine of u du. Now, here we have a bit of an issue. And the fact that you have to remember whenever you're doing u-sub, you're probably going to be dividing by that quantity. That tells me I don't want to use sine of u as my quote unquote u. I want to use cosine. Because if I use cosine, when I figure out what du is, that's going to cancel out my sine. It wouldn't cancel out my cosine. So I'm going to do u-sub, but I'm going to just use a different variable because it's easier for me to deal with. Let's say x is equal to the cosine of u. Then that means dx du, which feels weird, I 100% agree, is equal to the negative sine of u. So that means that du is equal to dx over the negative sine of u. So now we're going to replace du with this. And we're going to replace cosine of u with x. Notice how the signs will cancel each other out, right? When I'm dividing by this sign and this sign in here, those two are going to cancel each other out. So this looks like the integration. We have a negative 1 over x dx. And we know how to integrate 1 over x. That's just the natural log of x. Again, natural log of the absolute value of x. And let's make sure we keep that negative on the outside. Slap a plus c in there and we're almost done. Please remember, x is actually the cosine of u. So this becomes negative natural log absolute value cosine of u. Oof. Okay, let's look at this second one. This one's a little bit more difficult to deal with. This is dealing with secant of u. Now we know secant of u is equal to 1 over cosine, but instead we're going to do a lot of trickery for this. This is not something I expect you to do at all. No one's expecting this out of you. But if we were to instead multiply this whole thing by secant of u plus tangent of u on the top and bottom, that plus looks too much like a t. Then what we realize is we've really multiplied by 1, which is totally fine. We're always legally allowed to multiply by 1. And now instead of setting secant of u as our x, we'll say, hey, secant of u plus tangent of u is going to be our x in this case. That means dx du, well, what's the derivative of secant? It's secant u tangent u. And then the derivative of tangent is secant squared u. This gives me the following. Well, this will simplify down. This should be a plus inside. What will happen then is this gets replaced as u, right? We're going to change this to du equals dx over that whole thing, secant u tangent u, plus secant squared. And we realize that our numerator is going to cancel out perfectly with this. So this just became 1 over u. Oh, sorry. 1 over x. This is bad. Okay, for this, can you please leave? Please leave. Okay, for this next one. This one's a little bit trickier because we have a secant. There's not really a whole lot we can sub in here. So for example, what we're going to have to do here is we're actually going to have to multiply by 1. So secant of u ends up becoming the integral of secant of u times secant of u plus tangent of u all over secant of u plus tangent of u. I really hate using u as a variable here. This is a horrible idea. Du. Now, notice how this 100% is just 1, right? But that whole thing's just 1. And so instead, what we can do is now deal with this. We can say, hey, let's call x secant of u plus tangent of u. That means that dx du is equal to, well, what's the derivative of secant of u? That's just secant u tangent u plus, what's the derivative of tangent? Secant squared of u. And that means that du is just equal to dx over that whole thing. So secant u tangent u plus secant squared u. Notice if we were to multiply this whole piece out, if we were to multiply this, we would get secant squared plus secant tangent. So this whole thing simplifies down to 1 over x dx. And we know how to integrate 1 over x dx. It just becomes the natural log of the absolute value of x plus c. Now, our last step is we have to replace x with this, whatever we substituted out, which is secant of u plus tangent of u. So our final answer would be the natural log of the absolute value of secant of u plus tangent of u plus c. Whew. Which again is what we got here. I know you can definitely read that. That's what we got here. And you can use the same argument to be okay with the cosecant and the same argument to be okay with the cotangent. This is just another way to write it. I don't really foresee you guys having to use that too much, but it's something that if you have in your back pocket, it's really nice to do. I think we should be able to derive tangent and cotangent, but I think for the secant, it's a little bit trickier to deal with. It might be an easier thing just to memorize. Okay, in the next video, we're going to actually talk about evaluating some of these. So thank you for watching, and hopefully this next one will give you a little bit more practice. Bye-bye.